The name of this video is Toroidal Solenoid. First of all, let's remind ourselves what is a torus. A torus, in brief, is nothing but a donut, if you want. In particular, the tori which we're going to use in this course are donuts where the cream is located inside the donut somehow. It fills the donut, usually is vacuum, it's a vacuum space. The material of the donut itself, in our case, is going to be plastic or wood, and in Phys 342, eventually we are going to use this material, which is called the core of the torus, perhaps as ferromagnetic materials, because this toroidal construction is very useful to study the properties of, for example, any magnetic material, as we shall see again in Phys 342. So first of all, let's sketch our torus. In order to make a torus, how do we build it? Well, let's first of all sketch here a rotational axis oriented in this fashion, gamma z. So this is our revolution or rotational axis, okay? Vertical. Then let me sketch the torus here somehow. In sort of 3D. It looks something like this. There will be a central axis associated with this torus in green, as always. This is gamma. Let's take a cross-section of this torus, let's say here, for this meridian semiplane. I will come back to this concept in a few minutes. So as I said, the cream of the donut, in our case, is vacuum. So let's sketch it like this, where this region is full with material. There is vacuum inside and vacuum outside, and this axis goes within this vacuum region, okay, where the cream usually is located in a donut. So the torus is, if you want a donut filled with vacuum. You take this cross-sectional area here, this cross-section, and you rotate about the rotational axis, gamma z, the revolution axis, by 2 pi. And therefore you span the entire torus. For example, if you were to take a cross-section opposite to the center of the torus, which is somewhere here, this is the center O of the torus. So if you want to get it exactly on the other side, here, pi on the other side, we're going to have another cross-section similar to the previous one like this. Typically, we establish with the EMF a DC current inside this cross-section. We want to establish it in this way so that the current, the field eventually generated by this current goes according to the right-hand rule as gamma. So here it would go in this direction. So here it would go this way. And here it would go in my direction. Same direction, of course. This is my current I or J vector if you want. Okay? Like this. Great. So now we have the current which is associated with this object. Now, typically we choose a cylindrical coordinate system to represent as a coordinate system in this case, where this one will be the r-axis, this is the angle phi, this is the z-axis which coincides with the revolution axis gamma z, and this is the origin of our coordinate system, cylindrical in this case. In fact, many of the properties of this object are similar to the infinite straight line, except for translation, which we'll see in a minute, more in detail. So now we know how to build, how to make this torus. I told you that the core of this torus could be different type of materials. Let's say now it's wood, and I will come back in a minute on a more detailed discussion of how to make actually in real life such a device, okay, which is very useful. And so before doing that, of course, if I pick a point here, the tangent unit vector, we will call it t as always at this point, which in this coordinate system, of course, coincides with u phi, u bar phi. Great. So that's our construction. Now, before telling you how we make in real life and what are the conditions on this, the assumptions we typically do, let us discuss, as always, symmetries. Which are key to solve this problem. Very similar to the symmetries of the infinite straight line. The first symmetry, which is the same as the infinite straight line, is a rotation symmetry by any angle alpha about the gamma z axis itself. And so let's sketch that here. We have one sketch here, one sketch here. So the first one, let's do it right here. So let me do, as always in green, this axis. So let's do it a little bit smaller here. So let me condense it. Okay, this is our gamma z, oriented in this fashion, as always. Then let's only sketch the central axis of the torus. Okay, it's a simplification, just to make my life a little bit easier. This is just gamma. When I'm sketching here, let's remind ourselves of what is the current, let's say J, and we know that it has to go this way, so it will be going this way here, and this way here. My way here. So this is J in two spots exactly for these two cross sections we've seen here. This is the origin of the construction here of the torus, exactly as we've done there. So in this case, any rotation of any angle phi, so rotation, any angle bar phi about gamma z allows me to go, if I consider the whole construction as a rigid body, for example, if I had, let's say here, a point capital P, we have a vector field F. This will be the same at the point capital P prime up here. We will find the same vector field F upon making this rotation, in this case of pi, around gamma z. So, rotation of any arbitrary bar phi about gamma z. That's our first symmetry, okay? Same exactly as the infinite straight line. What about the other type of symmetry that we have for this object? Well, let's do the sketch here. Center. We want to keep it somewhere here. So this is our gamma, as before. This is our center, O, as before. This is our gamma z. This is O, this is gamma. Here we continue down here. So in this case, the rotation we want to use is a rotation by minus or plus pi. So rotation by minus or plus pi about the origin O. However, there is something here which is the same. So in the case of the infinite straight line for a charge distribution, we have a rotation symmetry. In the case of currents, we have usually anti-rotation. Let's see if this is the case also here. In fact, suppose that we have our current I in this direction here, or J, same thing. Now, let's also consider, as always, our point P characterized by a vector field, whatever that is, F, an arbitrary vector field. I perform this rotation, so I should expect a point capital P prime, a field exactly like this. But let's look what happens to this rigid body, to the current. When I do this rotation here, instead of getting a current like this, I get a current like that. So I get minus J. And because of this minus sign, exactly as for the infinite straight line, we have an anti-rotation because we need to change not only the change of sign of J, which means your EMF has effectively changed the sign of the current, so all the field generated by it have to be swapped as well. And so actually, we are going to end up here with this F at point capital P prime. So this is anti-rotation by minus plus pi above O. So these are the symmetries of this problem. That's the way the donut is constructed. How do we do it in real life, actually? The way we do this in real life, for example, if we consider here a part of this, like this arm here, let's say from here to here. So I just take that, and so I have something like that. Okay, this is continuous, obviously. I'm just zooming in this region here. So the way we do the wire, the torus itself, is to consider this as a core. So this is a core made of some material, let's say wood in this case, okay? And then we wind up around it a coil in the following fashion. Etc. Such that the current goes in this direction. This is my current, has to flow in this direction. So we want the current to go like that. That's my J. It goes in the direction of the axis here, which is again gamma. Okay, so we do it by winding a coil, like a copper wire, with a certain gauge around this, a tiny copper wire. We wind it around it, and that's the way we construct it. But there are some assumptions on these loops. So this is one loop of the wire, and so the assumptions are as follows. First of all, we have n loops, capital N loops, which we count. We can always count that. Second, we want n to be large in the limit plus infinite. In real life, just large, a large number. So we have many, many loops. And we want them to be equally spaced as much as possible. So very high density, equally spaced. This means effectively that we have one, let's look at it here. So suppose that I consider a semi-plane, for example, a plane crossing this in this direction. So I consider this semi-plane here. So this is called a meridian semi-plane, eventually continuous. Okay, it's a meridian semi-plane stemming from gamma z. If I do this, this simply means that I will have basically just one coil in this semi-plane, just one loop per plane, per meridian plane. This is what we are trying to do here. So that's the way you do it. You take basically a donut, which is made of wood, let's say, is a part of it, and then it looks like this, and you wind this wire around with these conditions here. So they are equally spaced in this fashion. Very important, that's exactly what we do in the experiment, as a matter of fact. And if you remember the coil in the radio in the very first lecture, there was a tube, which is an approximation of this. We'll come to that in a few minutes. In that case, the red wire which was going around was exactly the kind of wire. Okay, that was an infinite solenoid, approximately, but this is a degenerate case of that. Actually, that is a degenerate case of a toroidal solenoid, as we shall see in a few minutes in one of the next videos. All right, so now that we know that, it's also worth pointing out that typically in real life, the cross-sectional area the cross-section of this torus doesn't matter. So you can have, for example, cross-sections which look like this. So where this one is the region, this is the vacuum, and this is the cross-section, okay? Or you can have easier cross-sections like rectangular cross-sections, which is something very useful in calculations, and we will use it soon. So this is one of the cross-sections. One of these cross-sections can be rectangular, where in this case the current goes in this direction. So we want to go this way. Okay, and so let me be more precise here. I make a little bit, I mix up a little bit things always because that's the way it works with this thing. So you can either have a full conductor. Okay, so there are two things. Let's be careful on this. So this core can be a conductor, and then you establish a J which is uniformly distributed in this conductor, like I've done here. In real life, we don't do that. Okay, this is a simplification to make some simple experiments or some simple calculations. In fact, actually, the one we're going to use really in real life is going to be just like this. I mean, in the example we're about to do, it's just a filiform conductor where we don't even care about this cross section here, and there is a current J like this on it. Okay, so that's the limiting case. But in real life, typically we do just a wooden or something like this, or a ferromagnet core, and then we put this coil around. And so effectively, that's what we are doing in this picture here. Okay, so I hope this is clear. I hope the symmetries are clear. So to summarize, this is how we make a toroidal solenoid, which is a donut without cream, vacuum instead inside. This core can be a conductor, and you establish a J everywhere in it, or it can be a wooden core, and then you make a coil around it. These are the typical ways we do this device. We look at the symmetries, which are exactly the same for the infinite line of current, so rotation and anti-rotation symmetry. Sorry, rotation of any phi about gamma z and anti-rotation about O. There is no translation symmetry in this case, there isn't. Okay? And that's it.